Hello again, everyone. Thanks for joining us again as we take a bit of a deeper dive now into Yang-Mills theory. So remember, we're discussing Yang-Mills theory this year with a hope to understanding some of the great work that Karen Uhlenbeck has done. Max Orchard is joining us from the University of Queensland today. Max spoke to us last time about some of the basic content topics that we would cover in Yang-Mills theory, and now he's going to give us a bit more of the definitions that we can expect to see, hopefully culminating in the actual Yang-Mills equations that we're going to study. So thanks for that, Max.
Yeah, thanks, Tim. As you've just heard, last week, last time, not last week. Last time we essentially defined some of the more basic objects that we'll be studying. So principal G bundles and notions of principal connections. Now, I'll just do a quick recap on the definition of a connection. So suppose we have some smooth principal G bundle. So when we want to talk about connections, there's a few different things that we have to consider. So I'll fix a point P. The first thing that we need to talk about is the vertical subspace. At P, and it's simply the space of tangent vectors at the point P that are parallel to the fibers at this point P. So the vertical subspace is given to us by the structure of the principal G bundle. We don't get to choose what this vertical subspace is at each point. What we can choose is something called a horizontal subspace at each point. Now, a horizontal subspace is simply just a subspace of our tangent space so that the tangent space splits into the vertical and horizontal component. Now, if we make a smooth choice of horizontal subspace at every point, HP at each point, this is what we call a connection. I think we said Ehresmann connection, but I'm just going to drop the word Ehresmann for now. Just going to say connection. And finally, if the connection satisfies some sort of right invariance property, also I should note that the action of G on this principal bundle is a right action. If this is right invariant in the sense that if you multiply on the right by G, you get the horizontal subspace at PG. If this holds, then it is what we call a principal connection. Now, I'm going to just introduce a bit of notation here. The space of all or connections / principal connections is denoted with this fancy A here. It's kind of like a script A. And I'm going to write for for the horizontal and vertical components of a tangent vector or a vector field, I'm going to write vert of u or horizontal of u for the vertical or horizontal component of a tangent vector. Okay, so this is a nice geometric way of looking at connections. You know, you pick a subspace of your tangent space at each point, and there's some sort of smooth choice of this. The problem is that this can be a bit unwieldy to work with practically. If you have to keep track of all these subspaces of the tangent space, it can get a little bit not nice to work with. So the goal of this first part of the talk is to describe a more concrete way of looking at connections. And the way that we're going to do this is with something called a connection form. Connection forms. Okay, so first off, I'm going to introduce the notion of a fundamental vector field corresponding to an element of a Lie algebra. Suppose we have some element of the Lie algebra of the structure group. The fundamental vector field corresponding to X. And I've seen a whole bunch of different notations for the fundamental vector field. The one that I've seen the most commonly is some sort of like X hash, or I don't even know if this is a sharp, probably not a sharp, but I've seen this notation the most frequently. I've also seen a bar above the X. I've seen it below the X. I've seen a hat, all sorts of things. I'm just going to use X hash here. And this is given at each point by this guy here. Now we can sort of consider this fundamental vector field to be the infinitesimal generator of the action of our structure group on P, in the sense that, well, if we look at this exponential map and we're taking the derivative at time 0, we're essentially getting the sort of, the infinitesimal version of the action of G here. And the usefulness of this is that this actually induces, or this provides us with an isomorphism between the Lie algebra of the structure group and each vertical subspace. And we simply map X to the fundamental vector field at X at the point P. This is a linear isomorphism. Okay, well, the first thing to observe is that since the action of G preserves fibers, the infinitesimal generators of the action should be tangent to the fibers because we're preserving the fibers under the action. And the exact statement that you're tangent to the fibers is that you live in the vertical subspace at a given point. So it is true that the fundamental vector field at each point lies in the vertical subspace. The infinitesimal generators are tangent to the fibers, and that is exactly the statement that this lies in the vertical subspace. Now, I'm going to rewrite the definition of a fundamental vector field in a slightly different way. I'm going to define this smooth curve here. Now this is a smooth curve in our Lie group whose derivative at the identity is simply just x evaluated at the identity by definition. We can rewrite this as this here, where theta sub p is the orbit map. So where theta sub p, which goes from G to the fiber that P is contained in, and maps a group element to, well, this. And by definition of a principal G bundle, this is a diffeomorphism. Okay, and finally, we can rewrite this as, well, the differential of this point evaluated at the identity of this guy, just by definition. Okay, so from this, it follows that the mapping kappa is linear because we can rewrite it in terms of this derivative, this differential. So we know that it's linear. It suffices then to prove that this mapping is injective because, well, this is between finite dimensional vector spaces, it's linear. It suffices to just prove that it's injective. So finally, if your fundamental vector field is equal to 0, that's the same thing as saying that this evaluated at the point P, the fundamental vector field evaluated at the point P is 0 is the same as saying this at the point P. But we know that theta sub P, this orbit map, is a diffeomorphism by definition. So this implies that XE itself has to be 0 because the differential then has to be a linear isomorphism itself. And then finally, we conclude that X itself has to be 0 everywhere because it's left invariant. It's only determined by the value at the identity. So kappa is injective. And we are done. So this provides us with a identification between the vertical subspace at a point and the Lie algebra of the structure group. And this identification here provides us with a more useful way to view, or the more concrete way to view connections. Definition. So, given a connection, we define its connection form which I'm going to say is it's a one form that takes in at each point tangent vectors of P and is Lie algebra valued. So it gives you values in the Lie algebra. I'm going to explain a bit more what this means later. So essentially, this assigns to each P a linear mapping omega sub P, which goes from this tangent space into G. So the connection form itself is given by, if we look at a certain tangent vector at a point, we look at the vertical component of this, and then we look at, well, the identification of that vertical vector into in the Lie algebra. So this is the connection form for a connection. And a few quick remarks from the definition. The connection form sends you to zero if and only if you are a horizontal vector, because, well, if you have any sort of vertical component at all, your vertical component's not going to be zero, and because kappa is a linear isomorphism, you're not going to be sent to zero in the Lie algebra. So essentially, the way that we detect that we're a horizontal vector is that this connection form sends you to zero. And finally, it's also immediate that if we look at this connection form of a fundamental vector field, we just get x back by the definition of kappa and omega. So these are two immediate consequences of the definition. However, we can define this for any connection. And this whole connection form definition makes sense. If we want this to be a principal connection, it has to satisfy some sort of right invariance property as well, this connection form. And the right invariance property that this connection form satisfies is the following. We get that this, the P might be inside, is equal to the adjoint of this guy here. And I'm going to just label this with star. So this is the right invariance condition that principal connections have, but in terms of connection forms. So I'm going to split this proof up into two cases. The first case I'm going to consider is when U itself is a horizontal vector. Now, if U itself is a horizontal vector, then we can write the left-hand side of this guy here as this here. But because the connection is right invariant, we know that the right multiplication of U is also going to be horizontal at the point PG by the right invariance property, and omega kills horizontal vectors. So this is just going to be zero. However, that's also equal to this because, well, omega kills horizontal vectors. So omega sub P of U is zero. Therefore, this adjoint is also zero here. So it's nice and easy in the horizontal case. In the vertical case, it's a little bit more difficult. Case 2, U is a vertical vector. Okay, now if U is a vertical vector, I'm going to define a fundamental vector field such that at this point, it's equal to U. And we know that such a fundamental vector field exists because kappa was a linear isomorphism. So it's surjective onto the vertical space. A quick little computation before we get into actually proving the statement for vertical vectors. It's that if we act on the right of this fundamental vector field, what we get at the end is the fundamental vector field of the adjoint of X, evaluated at a certain point. Okay, so the proof of this lemma, we kind of just do some computations, play around with the definition a bit. So I'm going to look at it at the point PG inverse here instead. So this, by definition, is equal to this here. And then again, I'm just going to be essentially expanding out all these right multiplication maps. This is, by definition, equal to this. And I'm now going to combine all of these right multiplication maps into one. Oops, write that a bit neater. G inverse is going to be equal to this. And hopefully from here, it's immediate that this is going to be something related to the adjoint because we have conjugation appearing. So this is this, which is exactly the fundamental vector field of the adjoint evaluated at the inverse, because the inverse is the thing that comes first, of X evaluated at P. And this proves the lemma, because we can also just consider it at the point P as opposed to PG inverse. So yeah, this is kind of just playing around with the definition a bit. Nothing I don't think too enlightening here. So going back to the proof of the proposition, thus, if we look at this left-hand side of the identity here, by definition, we're equal to this at evaluated at the point, because by assumption, this is what this fundamental vector field does. By the lemma, we know that this is equal to the fundamental vector field corresponding to this adjoint. But because the connection form evaluated on fundamental vector fields just evaluates to exactly this, we've essentially gotten what we wanted. Now this is equal to this again, as U was equal to the fundamental vector field corresponding to X. So the connection form evaluated at U gives you just X back. So that completes the proof for case 2. And the general case immediately follows, because this identity star here, it's a linear, everything's linear here. And we can write any tangent vector as a vertical vector plus a horizontal vector. And we've proven it in both of those cases. So by the linearity of the star, this completes the proof. Yeah. Cool. So we've made all these constructions. Given that we have a principal connection, we've got this connection form. Now the question is, if we have some sort of connection form, can we recover a connection in the subspace sense from that? And the answer is yes, we can. So if we are given a Lie algebra valued one form here, satisfying the condition that you send fundamental vector fields to the element that generates the fundamental vector field for all x in G. we can recover a connection from this by setting the horizontal subspace at a given point to just be the set of all vectors sent to 0. Now, this in general isn't a principal connection, of course, but it turns out that if we also satisfy that right invariance property on the form, if in addition this form satisfies this right invariance property, this connection will also be a principal connection. So this formulation is an equivalent way of looking at connections. And it's a bit more concrete. So we're going to be using this formulation from now on. Now, I'm just going to give one quick example here. We looked at this thing in the last talk called the Maurer-Cartan connection. So we're going to look at a trivial G bundle. So it's globally a product. We know that the vertical subspace at each point is simply given by the tangent space at G to the group, because these are exactly what the fibers are. And the horizontal subspace we gave in the last talk to just be TPM. And we defined this to be the Maurer-Cartan connection. Cool. So the connection form for this, for the Maurer-Cartan connection will simply be given by, if we look at the map that we get at a given point in the trivial bundle, this is simply just going to be this map here. We're going to first project onto G and then take you back to the Lie algebra, essentially here. Now, hopefully it's clear that the kernel of this map is going to be the horizontal subspace because, well, if you live only in TPM, when you project down onto the G component, you're just going to be 0. And if you have any other sort of component in the vertical space, that is going to be preserved under the projection onto G. And then when you translate by this left multiplication, you're going to stay non-zero. So essentially, the kernel of this map is indeed TPM. And also, if we take some vector in this tangent space, we're going to verify the right invariance property here. So if we look at some H, which is going to be the thing we multiply with right invariance, this by definition is going to be this. But remember, the definition of omega is exactly LG inverse. Oh, sorry. LG inverse composed with this projection here. But because we're doing it at the point GH, we have to multiply by GH inverse when we look at this G inverse here. You can see this corresponds to G inverse. So when we evaluate this at GH, we have to look at GH inverse, which gives us this H inverse G inverse here. So finally, we can write this here, and inside you get exactly the Maurer-Cartan connection form at the point PG. And well, we have conjugation here. We're multiplying on the left by H inverse, on the right by H, and we're looking at the differential of these guys. So this is exactly the adjoint of H inverse of this guy here. So it satisfies the right invariance condition here. Now, this is the connection form for the Marat-Cartan connection. And I guess you could also verify, if you wanted to, that the fundamental vector field property is preserved, but I'm not going to do that here. I think it'd be fairly easy. Okay, a very brief aside into the world of Lie algebra valued forms. I'm going to pick, oh, that's a very bad curly bracket. I'm going to pick a basis for this Lie algebra of the structure group. We can write a differential form, a Lie algebra differential form. This is an R form here, as essentially a sum of real valued forms. These omega i's, these component forms, are real valued forms. Now, I think you can also put a tensor product in here somewhere if you want to be like very formal about this. This is the way that I think about it. It's kind of like the coefficient of this xi is given by a real valued form. And it's fairly easy to prove that this is, the constructions here are basis independent. So it doesn't matter the basis that you pick. All the constructions that we're about to give, it doesn't matter. So now that we have these nice real valued forms, we can define the exterior derivative of a Lie algebra valued form to be equal to, you can just ignore the Lie algebra value, or the Lie algebra part, the xi's, and just take the derivative of the real valued forms, which we all know how to do. And I'm also going to define this wedge product here to be kind of like the wedge product of the real valued forms, but we also have to do this multiplication here in the Lie algebra. And multiplication in the Lie algebra is essentially taking the Lie bracket. Now here I'm using some Einstein summation because it was a lot to write on one line. In particular, if both of these guys are one forms, because these correspond to connection forms and certain connection forms that satisfy certain properties. If this happens, then we can show that the wedge product of these two guys, I'm going to use y and z because we've already used x's, is equal to this here. And I think there might be a 2 somewhere here as well. I think there's a 2 out the front of this. It follows that the wedge product of a form with itself is actually given by this. And it's not actually, in general, equal to 0, as what you would expect with a with the wedge product. You would expect this to be 0, but it's not for one forms. It actually satisfies a sort of graded anti-commutativity property, where you have to look at the degree of your forms. But using these constructions, we get some very familiar properties for Lie algebra valued forms. For example, we get a graded Leibniz rule. On the exterior derivative, in the sense that if we look at this, this is simply given by this here. So for one forms, this degree is going to be 1. So for, in one form, this is just going to be a negative here. And similarly, there is this graded anti-commutativity of the wedge product here. Okay, so that finishes our brief aside into discussing some Lie algebra valued forms and the operations on them. The next thing that I want to discuss, which is quite important to Yang-Mills theory, is curvature of a connection. Now, when I say connection, I'm going to use connection form and the actual subspaces very interchangeably here because they're completely equivalent here. And for most, I think for all of these connections now, I'm going to assume that they're principal connections. I don't really want to have things that aren't compatible with the group action on this principal bundle. Okay. So suppose we have a connection and let phi be a Lie algebra valued R form. So now that we have this connection, I'm going to talk about something called the exterior covariant derivative. Now, it's denoted by D sub A. And I guess this would go from x1 up to xr plus 1. And this is simply just, well, the exterior derivative of this guy, but we're only going to be evaluating in the horizontal direction. Like this. So essentially, what this is saying is, how does this form phi change in the horizontal direction? If we apply this covariant derivative to the connection form, oops, that should be a phi here. These should be phi's. If we apply this to the connection form, for A, then its curvature form, which I'm going to denote with F sub A, and this is going to be a Lie algebra valued 2 form, is given by the covariant derivative of the connection form itself. So essentially, what this is saying is, how does the connection itself change in the horizontal direction? If the connection itself changes just a little bit as you go in the horizontal direction, your curvature is going to be small in some sense. This is going to give you a small curvature. But if in the horizontal direction you change a lot, you're going to get, in some sense, a large curvature. That's supposed to say theorem. So we have this definition of a curvature form, a little bit unwieldy to work with again. Luckily, there is a formula that makes things a little bit easier to work with, which is called the Cartan structure equation. And you might have seen this before in the context of real valued forms. If you have some connection A, then the curvature form for this connection satisfies this. Here, where omega, of course, is the connection form associated to the connection A. Now, we can rewrite this as this as well, using the properties of the wedge product that we defined earlier as well. Now, I'm not going to provide a proof of this statement. You can do it in a very similar way to, and considering the vertical vectors, the horizontal vectors, and a combination of vertical and horizontal for x and y, because everything here is linear, but it's a bit tedious and computation heavy. So I'm going to just ignore the proof of that for now, and you're just going to have to trust me on that. What I am going to prove, however, is a pretty important identity that the curvature form satisfies, and it's that if you take the exterior covariant derivative of the curvature, you're just going to be left with 0 itself. Now, the proof of this, I'm going to start actually by the structure equation that was given in the last theorem. We know that the exterior derivative of, well, not the covariant derivative, just the exterior derivative here, I believe. This is going to be given by the exterior derivative of this here. This is exactly the structure equation. And applying this to each term separately, the first term is clearly going to be 0 because we're applying the exterior derivative twice. And for the second term, we're going to use the graded Leibniz rule. Well, these are all one forms, so we're just going to get a subtraction here. We're going to get d omega wedge omega minus omega d omega, like this. This is just using the Leibniz rule. Thus, if we want to evaluate this at some vector fields x, y, and z, by definition, this is equal to the derivative of this guy, but only looking at the horizontal components of all these vector fields. And by the above, this is equal to this here evaluated at the horizontal components. But omega sends horizontal vectors to 0. So in both of these wedges, we're going to be having omega of horizontal components. And that makes everything here 0, as omega of anything horizontal is equal to 0. Cool. Now, this is satisfied by every connection and every curvature form. However, Yang-Mills theory goes a little bit further than just the Bianchi identity. We're almost there. And we're just about to look at the Yang-Mills equation. So first off, a connection is flat if, well, hopefully this definition makes sense, your curvature is identically zero everywhere. Now, an example of a flat connection is the Maracatan connection that we gave earlier. That is a flat connection. If you do the computation, you'll find that you just get zero at the end for the curvature. And if you look at the Cartan structure equation, it turns out that the Maracatan connection plays a very crucial role in all flat connections. The connection A is flat if and only if there exists a local trivialization U alpha phi alpha covering the base manifold M such that the connection form restricted to, well, where this locally looks like a product is actually itself induced by the Maracatan connection on the trivial U times G. And I guess it has to be induced through a map here. It has to be induced through this trivialization phi alpha. Now, a corollary of this, now what exactly this corollary is saying, I guess, the exact words aren't too important. A principal G bundle admits a flat connection if and only if there exists local trivializations U alpha phi alpha covering M such that the transition functions now that go from U alpha, these intersections, to G are constant. Now, to be honest, I don't really know what these transition functions actually are, but the main takeaway that I want to give here is that it is not always possible for a principal G bundle to admit a flat connection. So instead, what we're going to try and do is choose a connection that has in some sense, minimal curvature. The goal now is to choose a connection that, in some sense, minimizes the curvature. Because we can't get it to be zero all the time. We want it to be as small as possible, essentially. Now, such connections are Yang-Mills connections. So how do we find Yang-Mills connections? And what do we mean by minimizing the curvature? So here, I'm going to now say that the base manifold M is going to be endowed with, I guess, a pseudo Riemannian metric, because I guess if we're in physics, we want to look at Lorentzian metrics as well. So we need to also consider the case where we have pseudo Riemannian metrics. When we have this induces a a bilinear form on differential forms. The word form here is used in two different contexts. So in this sense, I'm going to say that the norm squared of the curvature, which I'm going to define to be this kind of thing here, is the trace of the curvature wedged with the Hodge star of this guy. So essentially, we're completing it to a volume form, and we're taking the trace. This here is a map, a smooth map between M and R. It's real valued. Now, the squared here is, it's a little bit misleading because if this metric here is actually pseudo-Riemannian, I might just say the metric itself is G. If G is pseudo-Riemannian, this guy might actually be negative at times. So when you see the squared, don't think that it has to be non-negative. If it's pseudo-Riemannian, it could be negative. So now that we have this, I'm going to define the Yang-Mills functional. Now this is the map. I'm going to call it Ym. That takes in a connection and spits out a real number. Now this norm, L2 norm, I guess, of the curve, this norm of the curvature is at each point. Now, if we want to get the overall, I guess, size of the curvature, what we're going to do is we're just going to integrate this over the entire manifold, the entire manifold here. And this will give us, I guess, the total connection, total curvature of the connection at every point. And the idea is, if we want to minimize curvature, we want to minimize the value of this Yang-Mills function. And the way that we're going to do this is, look at a slight perturbation of a connection, compute the derivative, find the critical points, bit sort of calculus of variations kind of style, I guess. Now, a quick remark is that this is actually an affine space. Modeled on this vector space here. The main reason I'm saying this is to make the notion of adding connections sound. It's not entirely important for what I'm going to say. But essentially, if we have a connection and we add a slight perturbation to it, and we take this derivative at t equals 0, this is given by this here, where we have the formal adjoint. Now that we have a bilinear form on differential forms, we can consider this formal adjoint of the covariant derivative. So essentially, I'm just going to very quickly go through this proof. If we want to look at the curvature of such a perturbed connection, it turns out that you get, by the structure equation, you get something like this. Like this. And when you expand everything out, you get the curvature of A back alongside this, alongside this, just by linearity of things. You can pull T's out the front, that sort of thing here. Thus, if we want to look at the Yang-Mills functional of this perturbed connection, well, this is going to be equal to this integral here of just by the linearity of everything here, is going to be the norm of the original curvature plus some sort of perturbation here. We get 2t FA DAA plus some higher order terms that are going to disappear when we differentiate and evaluate at t equals 0. So we have this here. Essentially, hopefully you can believe this statement here. If you just expand out what the curvature is in this bilinear form and use bilinearity, you're going to get exactly this. Now, once you compute this derivative, you're just going to get this. And the claim immediately follows just by the definition of this formal adjoint. Cool. Now, it follows that the minimizers of this Yang-Mills functional have to satisfy this derivative being equal to 0 for every A. So Yang-Mills connections satisfy this derivative A plus TA, which is equal to this. Oh, that should be an A. D vol G is equal to 0 for every A. And that is, it satisfies the so-called Yang-Mills equation. Is, if you look at this adjoint of derivative of the curvature, it itself is equal to 0. This is the Yang-Mills equation. And it follows from just what we said above, if you have a Yang-Mills connection. That is, a Yang-Mills connection actually satisfies two equations that involve the differential equations. It satisfies the Bianchi identity, which is just this derivative equals 0. And finally, the adjoint is equal to 0. A Yang-Mills connection satisfies both of these. Now, I'd like to compare this to harmonic forms. Or forms, omega, that satisfy this exact condition here. Now, in a sense then, Yang-Mills theory is very similar to Hodge theory. And in Hodge theory, we look at a differential form and we try to find a harmonic representative in the de Rham class of this. Essentially, Yang-Mills theory is looking at a harmonic representative in the space of all possible connections on your principal bundle, in the sense that you have to satisfy these two differential equations that involve the covariant derivative and its adjoint being equal to 0. Okay, there was one other example that I wanted to go over about how you can actually recover Maxwell's equations from this, but I think I'm out of time, so I'm going to not do that. So thank you, everyone.
Let's thank Max for taking us through some of this content. Yes, thank you, Max. Does anyone have any comments or questions for Max now that we've arrived at the actual Yang-Mills equations that we want to study?
Yeah, I have a question. Hi. So
Yes,
yeah, thanks, Max. Yeah, thanks, Max, for the lecture. I just want to ask, can you clarify what you mean by the trace on the previous slide? Oh, sorry, one before. Yeah, what do you mean by the trace?
Well, I guess this is going to be a linear map still, right?
Yeah, I mean, you have a volume form, but the values are at the algebra. So what do you mean by the trace?
That's actually a good point. I hadn't thought of that.
I think
Yeah,
I've
gonna
seen
be
this
real value.
notation if
What
you
do
like
you,
specify.
if
I
you
think I've seen
specify a
this notation if you
basis, maybe you get those real
Yeah.
valued forms, like
Like
what
if you,
I suggested back
like a killing form.
here, like where you specify these real valued forms. And I guess it's basis independent, the trace, so you're probably going to get something real valued if you look at these real valued forms.
Well, I mean, you have n forms, not a matrix, right? So what do you mean by trace?
Yeah, I think that this is, yeah, you just somehow get a some sort of linear form based on the real valued guys. And yeah, I'm not entirely too sure actually myself about this.
Yeah. Okay. I think I've seen somewhere that you like specify the group to be, for example, like SU, and the trace is the trace in SU, right?
Okay, sure.
So I think if you specify a Lie group, I guess it makes sense, like a matrix Lie group.
So if we specify a structure group, we know what the Lie algebra is then of that guy, and then we take the trace in the Lie algebra. Do we require then that it's a matrix group or something?
I think if you write as a trace, you probably should, but generally you just use a killing form in the Lie algebra.
Okay, yeah, that makes sense. You can just use a killing form.
I think. Yeah, but I got just a bit confused. Thanks.
Thanks for that very probing question, Stefan. Does anyone have any other comments or questions?
So the Maxwell equations look more or less the same. So what's the relation between this and the Maxwell equation?
So the Maxwell equations appear when you take the principal U1 bundle over R4 and you specify a certain connection that sort of captures the electric and magnetic fields. If you look at this and endow R4 with the Minkowski metric, this will give you the what you need for the adjoint. It turns out that the Bianchi identity gives you two of Maxwell's equations based on this connection, and the Yang-Mills equation gives you the other two of Maxwell's equations for electromagnetism.
Max, perhaps you could write them down just in terms of curl and divergence real quick.
Yes, I've got that on a page here. So this equation gives you these two. This and this equation gives you this if you look at a specific minus. If you look at a specific connection.
Max, you've got time evolution here, but I guess the point is the Yang-Mills equations themselves are just static.
Yes.
So perhaps you don't have the time derivatives in that equation?
Let me check. I've got the thing up here.
Like I guess Maxwell's equations would be like the Yang-Mills flow, right?
I guess this comes from, I guess, R4 having being one of the coordinates being time.
Oh, I see, of course.
Yes.
No, yeah, you're right.
That up real quick. Yeah.
Oh, I see. Yes, the Minkowski metric.
Yes. So we have the Minkowski metric. It's pseudo-Riemannian, so we might get negative norms here, but yes.
Oh, great.
I see. Thanks.
Awesome. Maybe we can leave it there. Let's thank Max again for taking us through all of this stuff. Right, that'll do us for today. Please stay tuned, and we'll eventually we'll announce when our next talk will be, and we'll continue talking about all of the theory of Yang-Mills equations. Thanks, everyone.